Okay, so that is equal to 200. And our shear stress, this is 50, 100, 150. Element rotate clockwise. 0 minus 50 minus 100. I think I better push it up slightly. Minus 150. Okay. And I'll do the negative side up to 100. And we know last week we drew a box, right? The operating boundary. So we're going to draw the box again. So we know that it's 50 in shear, and Tresca assume that positive and negative stresses or tensile and compression are the same. So I'm going to draw a box now, right? And if the stress field or if the Mohr circle in 3D are within the box, the structure will not fail. Okay, if it does not, it will fail. Okay, so you can see for this case, right? So let's do X, Y, and Z. So let's say this is our X, this is our Y, and then this is our Z. Okay. If we just plot X and Y, right? So it's 1 point is at 150, right? So this is your point X, and then 25 is your point Y. Okay. And then if you just draw this circle, right? You realize that the circle is outside the operating boundary already, right? But it gets worse, okay? So this is only for your XY plane, which is your in plane. So we learned this last week, yeah? Okay. And then we know that this is point Z, right? This is point Z. And then we can draw another circle. And this is your what? YZ plane, right? Which is your out of plane, right? Out of plane. What is even worse now is there's another circle that we're going to draw. So let's say if you were to ignore 3D Mohr circle, the material will already fail. But the magnitude of failure is not that big because the shear stress for now is, if you look at this, the shear stress, I'm just so it's 150 minus 25 divided by 2 is 62.5 megapascal. But in reality, it's bigger than that. Okay, when you construct 3D Mohr circle. So there's another circle that we have to draw when we do 3D analysis, okay? And when we do 3D analysis, right, it will be equal to what? This is the big circle. Right, so this is for your X, Z plane, and this is your out plane. Right, so the failure, the true failure now, okay, based on analysis over here, this is what? 75 megapascal. Okay, if you just do 2D Mohr circle, okay, the biggest diameter over here is equal to 62.5. Okay, now you will ask me, Eugene, why is it so important to know this value? Because if we were to calculate the factor of safety in shear, right, we have to know this number. Okay, or if you're going to pick material, okay, if you only do 2D Mohr circle, which is only using the XY plane, you realize that, oh, maybe my material only can need to withstand 62.5 megapascal worth of stress. That's not true. Okay, the true value is what? 75. Okay, so this is one case. So the material will yield already because this portion of the Mohr circle is outside the what? Is outside the box. At any time when it's outside the box, right, the structure will yield. Okay, as long as any of the circle go outside, it will yield. Okay, now let's look at another example. Okay, so this example, okay, a different stress state. Okay, let's look at a different stress state. And I want to show you how critical is 3D Mohr circle in this. Okay, let's look at another stress state. Okay, so this is our, so again the same, the stress is 100. Okay, so this is our X, and this is our Y, and this is our Z, and we do 3D Mohr circle again. Right. So now we declare that we have a compression of 75 megapascal. And then we have a tension of 25 megapascal, right? And then our stress Z is equal to 0. Okay, let me, our stress Z is equal to 0. Okay. Or hold on. I want to show, yeah, our stress Z. So you can see all these values are less than what? Are less than 100, plus or minus 100 megapascal, right? But we have to be very, very cautious, okay? And when we, again, we have to draw 3D Mohr circle with this, okay? And then you see what happened. So again, okay, so this is our normal stress, shear stress, okay? So this is 50. Oh, I'm going to draw 25, 50, 75. Okay, I'm going to move this to get 100, so I can draw the box. Normal stress 0, 25, 50, 75, minus 100 over here. And then 25, 50, 75, minus 25, minus 50, minus 75. Okay, so one of the stress is at negative. So let me draw the box first. Okay. Okay, so this is the box. So based on normal stress, right? So this is our point X. Oh, let me change color. Point X, point Y, and point Z. So we know that this is our point X, right? And this is our point Y. But both of them happen to be inside the what? Inside the box, right? So when you were to draw, okay, draw the box, right? So now we can draw the circle now. Right? We realize that the material will not fail, right? And then, so we know that this is our XY plane. And then over here, this is your point Z, right? And then you have to ensure. Now, the other two circles, you have to still draw it to ensure that it's inside the what? To show that it's inside the box. Okay, so for this case, it's still our YZ plane. And the final circle, okay, so this is our final circle, and this is your exact plane. Okay, so you realize that now when all the three circles are inside the box, we know that the structure will not what? Will not fail. It has to be all the three circles. Okay. So the next thing I'm going to do is we are going to look at the operating bracket. Okay. So we are going to look at the operating bracket for Tresca criteria before we go into example. Okay, so we have to look at the operating boundaries for Tresca criteria. So now I'm going to draw a different graph now. Right. So on the x-axis now, okay, and then we have our y-axis, right? So this is our stress A axis. Right. Over here, this is our stress B. So stress A and B, I should not put a circle. Okay, I do apologize. So stress A and stress B are the principal stresses. Okay. So if this is 100, or this is, yeah, I'll put it 100. This is minus 100. Over here, this is 100. And this is minus 100. Right. So Tresca criteria, the operating boundary looks like this. Now this is stress A and stress B, yeah? It's not normal stress and shear stress, okay? So this is how Tresca criteria look like. Okay. So just give a